This is Sleepy Space, a slow space story to help you fall asleep. Most people think they know what the Milky Way is. They've seen it before, a pale band of light stretching across the night sky. Soft, diffuse, almost cloud-like. If you're far from city lights, on a clear night, it's impossible to miss. For thousands of years, humans have looked up and seen the same thing. They gave it names. They told stories about it. They tried to explain what it meant. The ancient Greeks called it the Milky Way because it looked like spilled milk across the darkness. The Romans called it the Road of Souls. Other cultures imagined it as a river, a path, a bridge between worlds. It feels distant, comforting, something out there. But that feeling is wrong, because the Milky Way is not something you look at. You are inside it, right now. You are not observing a galaxy from afar. You are embedded deep within one, surrounded on all sides by stars, gas, and dust, so completely that your eyes can only see a thin cross-section of it projected onto the sky. That faint band of light is not the galaxy itself. It's what the inside of a galaxy looks like when you're trapped within it. And that changes everything, because once you realize you're inside something this vast, a new question appears. If this is our home, how big is it really? And where exactly are we inside it? From Earth, the view is deeply misleading. On a perfect night, under perfect conditions, you might see a few thousand stars. In most places where people actually live, far fewer. Streetlights, buildings, car headlights. They wash out almost everything. Even in complete darkness, even if you could somehow see every star visible to the human eye, you would still be seeing almost nothing. For every star you can see, there are tens of millions you cannot. Most are too faint, too distant, or hidden behind vast clouds of gas and dust that block their light. What your eyes show you is not the galaxy. It's a suggestion of the galaxy. A thin slice of something far larger than human intuition was ever designed to understand. For most of human history, this illusion was all we had. The stars seemed fixed in place, their patterns unchanged night after night, century after century. Orion looked the same to ancient astronomers as it does to you. The Big Dipper has not shifted in recorded human history. A few objects moved. The planets wandered slowly against the background stars. The moon shifted from night to night. The sun traced its daily arc across the sky. But the Milky Way remained a mystery. It wasn't until telescopes were invented that the illusion began to crack. When Galileo first pointed a telescope toward that pale band of light, he made a discovery that quietly rewrote humanity's place in the universe. It wasn't a cloud, it wasn't mist, it was stars. Thousands upon thousands of them packed so tightly together that their combined light blurred into a continuous glow. This meant the Milky Way wasn't separate from the stars. It was made of them. But even then, we still didn't understand the truth. It would take centuries more to realize that the Milky Way wasn't just a cluster of stars in the sky. It was a structure, a galaxy, a rotating disk of hundreds of billions of stars, stretching so far across space that light itself takes tens of thousands of years to cross it. And we were not near the center. We were not near the edge. We were buried deep inside it with no way to step outside and see the full shape. Imagine trying to understand the shape of a forest while standing between the trees. Every direction looks crowded. Every path looks similar. Distance becomes impossible to judge. That is our situation. We live inside a galaxy so vast that even our most powerful instruments struggle to map it. A structure so large that the light from its far side began its journey toward us before modern humans existed. And yet, this is home. To understand what the Milky Way really is, how big it is, where we are inside it, and what it means to live in a place like this, we need to begin a journey. Not outward from the galaxy, but outward from where you are right now. Here, on Earth, the stars you see aren't evenly distributed across the sky. If you could count them carefully, you'd notice that most stars are concentrated in or near that band of light. There are fewer stars as you look away from the Milky Way. And if you look directly perpendicular to the band toward what astronomers call the galactic poles, there are very few stars at all. This distribution is a clue, a hint about the shape of what we're inside of. But we're getting ahead of ourselves. Let's start the journey properly. Let's leave Earth. The planet you're standing on right now is your reference point. It's home. It's the only place any human has ever lived, except for brief visits to the moon. Everything you've ever experienced happened here, within a few kilometers of Earth's surface at most. Earth is about 12,700 kilometers across, about 7,900 miles. That's the diameter at the equator. If you wanted to walk around the world following the equator, you'd travel roughly 40,000 kilometers, or 25,000 miles. Walking 8 hours a day at a steady pace, it would take you about 3 years. This is human scale, this is distance we can comprehend. Long, yes, but achievable. People have walked across continents. Sailors have circumnavigated the globe. These are journeys measured in months or years, but they're within human capability. Now, we're going to leave this familiar scale behind. We're going to start expanding outward, and the distances are going to get larger in ways that challenge comprehension. The Moon orbits Earth at an average distance of 384,000 kilometers, about 239,000 miles. Light takes 1.3 seconds to travel from the Moon to Earth. When astronauts on the Moon spoke to Mission Control in Houston, there was a noticeable delay. They'd say something, and 1.3 seconds later, their words would arrive. Then Houston would respond, and 1.3 seconds later, that response would reach the Moon. Every conversation had this strange rhythm, this delay built into it. The Moon is the farthest humans have ever traveled. 12 people have walked on its surface. The last ones left in 1972. Nobody has been back since. From the Moon, Earth looks like a blue and white marble hanging in the blackness, small enough to cover with your thumb if you held up your hand. All of human history, every person who's ever lived, visible as a small sphere. You can see continents and oceans and clouds, but you can't see cities. You can't see individual features. Earth becomes one object instead of the familiar ground beneath your feet. This shift in perspective matters, because once you leave Earth, once you look back at it from a distance, it stops being the whole world and becomes a world. One planet. Not the center of everything, but one object among many. Keep going. Moving outward from the Moon, we pass through the region where satellites orbit. Communication satellites, weather satellites, the International Space Station. These orbit between a few hundred and a few tens of thousands of kilometers above Earth's surface. From this distance, Earth still fills much of the sky. It's still clearly the dominant object, still obviously home. But we're not stopping here, we're going farther. At about 30,000 kilometers out, a little less than a tenth of the way to the Moon, you'd cross through Earth's magnetosphere. This is where Earth's magnetic field stops deflecting the solar wind, the stream of charged particles flowing out from the Sun. Beyond this boundary, you're in interplanetary space. Earth starts to shrink behind us. By the time we've traveled 1 million kilometers, about 2.5 times the Moon's distance, Earth is just a bright blue star against the darkness. You'd need a telescope to see continents. At 5 million kilometers out, Earth and Moon would look like a double star. 2 points of light close together, one blue, one grey. This is still nothing. We haven't even begun to leave Earth's neighborhood. The Sun is 150 million kilometers away, about 93 million miles. This distance is called an astronomical unit, or AU. It's one of the basic measuring sticks of the solar system. Astronomers use it because it's convenient. Earth orbits at 1 astronomical unit by definition. Mercury orbits at about 0.4 astronomical units. Mars at 1.5 astronomical units. It's easier than using millions or billions of kilometers for everything. Light takes 8 minutes and 20 seconds to travel from the Sun to Earth. When you look at the Sun, you're seeing it as it was 8 minutes ago. If the Sun exploded right now, we wouldn't know for 8 minutes. We'd keep seeing the Sun, feeling its warmth, completely unaware that it had changed. Then, 8 minutes later, the light would stop arriving and we'd know something had gone wrong. From the Sun, Earth would be barely visible, a tiny blue dot against the vastness of space. You'd need a decent telescope to see it at all, and even then, it would just be a dot. No visible features, just a point of reflected sunlight. The Sun dominates the inner solar system. It contains 99.86% of all the mass in the solar system. All the planets, all the moons, all the asteroids and comets, everything else combined accounts for less than 0.15% of the total mass. The Sun is the anchor. Everything else orbits around it, held in place by its gravity. But as we move outward from the Sun, its light grows dimmer. Its gravitational pull weakens. The distances between worlds grow larger. Venus orbits at 0.7 astronomical units. From there, the Sun appears about twice as large and bright as it does from Earth. Mercury, at 0.4 astronomical units, sees a Sun that's 2.5 times larger. But move outward and things change quickly. Mars orbits at 1.5 astronomical units. From Mars, the Sun is noticeably smaller, about 2/3 the apparent size you see from Earth. Sunlight is weaker. Days are dimmer. The sky, when dust storms aren't raging, is a butterscotch color because Mars's thin atmosphere scatters light differently than Earth's. The asteroid belt lies between 2 and 3.5 astronomical units from the Sun. Despite what science fiction suggests, it's mostly empty space. The asteroids are spread out over such a vast volume that you'd have to aim very carefully to hit one. If you were flying through the asteroid belt, you probably wouldn't see any asteroids at all, unless you went looking for them. At 5.2 astronomical units, we reach Jupiter. The giant planet, 11 times Earth's diameter, massive enough that 1,300 Earths could fit inside it. From Jupiter, the Sun is just a fifth as large as it appears from Earth. Sunlight is 25 times weaker. Days are dim, twilight-like. Jupiter has 95 known moons. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610. They orbit Jupiter the way planets orbit the Sun, visible even through a small telescope. Europa, covered in ice, might have an ocean beneath its frozen surface. Ganymede is larger than Mercury. Io is the most volcanically active body in the solar system, its surface constantly being reshaped by eruptions. This is already an alien environment. We're an hour's light travel time from Earth. Messages take an hour to reach this distance, traveling at light speed. An hour to send a signal, an hour to get a reply. 2 hours for any conversation. Saturn orbits at 9.5 astronomical units, nearly twice Jupiter's distance. The Sun is now 1/100th as bright as it appears from Earth. Saturn, with its magnificent ring system, takes 29 years to complete one orbit. The rings, made of countless chunks of ice ranging from grain-sized to house-sized, orbit the planet in a disk thinner than the distance from New York to Los Angeles, despite being wider than the distance from Earth to the Moon. Titan, Saturn's largest moon, has a thick atmosphere. Lakes and seas of liquid methane and ethane cover parts of its surface. It's the only moon with a substantial atmosphere, the only body besides Earth known to have stable liquid on its surface. That liquid isn't water, it's methane. Cold enough at Titan's distance that methane behaves like water does on Earth, cycling between liquid and gas. Uranus orbits at 19 astronomical units. The Sun is now just a very bright star, noticeably smaller than it appears from Earth. Uranus is tilted on its side, rolling around its orbit like a barrel. Its poles take turns pointing at the Sun, creating seasons that last decades. The northern hemisphere gets continuous sunlight for 42 years. Then continuous darkness for 42 years. Neptune, the outermost major planet, orbits at 30 astronomical units from the Sun. Light from the Sun takes 4 hours to reach Neptune. From Neptune, the Sun is 900 times dimmer than from Earth. Still bright, brighter than the full moon appears from Earth, but clearly a point source now. A star, not a disk. Neptune takes 165 years to orbit the Sun. Since its discovery in 1846, it has completed only one orbit. It will not return to the position where it was discovered until 2011. And yet, we are still in the Sun's neighborhood. We have not even left the solar system yet. Beyond Neptune lies the Kuiper Belt, a region of icy bodies stretching from about 30 to 50 astronomical units. Pluto orbits here, along with thousands of other objects. Pluto, demoted from planet status in 2006, is just one of many similar-sized bodies in this region. The largest known, Eris, is slightly smaller than Pluto, but more massive. These are cold, dark worlds. Sunlight at this distance provides about 1,000th the illumination we get on Earth. Surfaces are frozen harder than rock. Temperatures hover around -220 degrees Celsius. The scattered disk extends even farther, reaching perhaps 100 astronomical units from the Sun. Objects here orbit on highly elliptical paths, swooping in towards Neptune and then back out into the darkness. And beyond that, the Oort cloud, a theoretical shell of icy bodies surrounding the entire solar system. It might extend as far as 100,000 astronomical units from the Sun. Maybe 200,000 astronomical units. We are not sure because we have never directly observed it. It is too far, too dark, the objects too small and faint. But we think it is there because of comets. Long-period comets, the ones that take thousands or millions of years to orbit the Sun, seem to come from random directions in space. The best explanation is that they are falling in from a vast cloud of icy bodies surrounding the solar system. At 100,000 astronomical units, you are about 1.6 light-years from the Sun. Light takes 1.6 years to travel that distance. The Sun is just a very bright star now, noticeably brighter than any other star, but not obviously special. If you did not know better, you might not realize it was the same object that dominates Earth's sky. And this might be the edge of the solar system, the outermost reach of the Sun's gravitational influence, the boundary between what belongs to the Sun and what belongs to the galaxy at large. We have traveled 100,000 times farther than the distance from Earth to the Sun, and we are still, technically, in the solar system, still within the Sun's domain. This gives you a sense of how empty space is, how much nothing there is between the somethings. The solar system is mostly empty. Tiny islands of matter, planets and moons and asteroids, separated by vast oceans of vacuum. 2 spacecraft have left the solar system. Voyager 1 and Voyager 2, launched in 1977. They have been traveling for over 45 years now, moving at about 17 kilometers per second. That is fast by human standards. Fast enough to cross the United States in about 5 minutes. Voyager 1 is now about 24 billion kilometers from the Sun, about 160 astronomical units. It crossed into interstellar space in 2012, passing through the heliopause, the boundary where the solar wind stops and the interstellar medium begins. At its current speed, Voyager 1 will take another 300 years to completely leave the Oort cloud. Then, it will drift through the space between stars for thousands of years before it comes anywhere near another star. This is the scale of the solar system, vast beyond everyday comprehension, yet tiny compared to what lies beyond. Because now we need to talk about distance on a different scale. Now we need to talk about light years. A light year is the distance light travels in 1 year. Light moves at 300,000 kilometers per second. Nothing can travel faster. It is a fundamental speed limit built into the structure of the universe. In 1 second, light travels 300,000 kilometers, enough to circle Earth's equator 7.5 times. In 1 year, light travels 9.46 trillion kilometers. That is 9.46 with 12 zeros after it, about 5.88 trillion miles. This is the distance we use to measure the space between stars, because kilometers, or even astronomical units, become unwieldy at these scales. The numbers get too large to work with easily. The nearest star, Proxima Centauri, is 4.24 light-years away. That's about 40 trillion kilometers. 268,000 astronomical units. If you compress the solar system down so that the distance from the Sun to Neptune, 30 astronomical units, was represented by 1 inch, Proxima Centauri would be about 150 feet away. That's how far apart stars are, not inches apart, not feet apart. The distance between stars is measured in light years, in trillions of kilometers, in incomprehensible emptiness. Proxima Centauri is part of a triple star system called Alpha Centauri. The other 2 stars, Alpha Centauri A and B, are larger, Sun-like stars that orbit each other. Proxima orbits the pair at a distance of about 15,000 astronomical units. That's about a fifth of a light year. From Earth, Alpha Centauri A and B look like a single bright star in the southern constellation Centaurus, third brightest star in the night sky. But they're actually 2 stars, orbiting each other every 80 years, separated by distances that vary from about 11 astronomical units to 36 astronomical units. Closer together at their nearest approach than Saturn is from the Sun, farther apart at their farthest than Neptune. Proxima Centauri is much smaller, a red dwarf only about an eighth the Sun's mass, a seventh its diameter. It's so small and dim that you need a telescope to see it, despite being the closest star to Earth. It's also a flare star prone to sudden brightening as magnetic activity on its surface releases energy. We know there's at least 1 planet orbiting Proxima Centauri. Proxima b, discovered in 2016. It's about 1.3 times Earth's mass, orbiting every 11 days at a distance of about 0.05 astronomical units. Because Proxima Centauri is so dim and cool, this puts Proxima b in the habitable zone, the range where liquid water could potentially exist on a planet's surface. Whether Proxima b is actually habitable is another question. Being so close to a flare star means it's probably bombarded by radiation during flares. It's likely tidally locked, always showing the same face to its star. One side in permanent daylight, the other in eternal darkness. Whether life could arise and survive in such conditions, we don't know. But the point is, there's a potentially Earth-like planet orbiting the nearest star. If we ever develop the technology to travel to other stars, Proxima b would probably be the first target. With our current technology, getting to Proxima Centauri is impossible. The fastest spacecraft we've built, the Parker Solar Probe, travels at about 190 kilometers per second. At that speed, it would take about 6,800 years to reach Proxima Centauri. That's longer than all of recorded human history. You could have launched a spacecraft toward Proxima Centauri when writing was first invented, and it would still be in transit today. There have been proposals for faster spacecraft, tiny probes accelerated by powerful lasers to perhaps 20% of light speed. At that speed, a probe could reach Proxima Centauri in about 20 years. Add 4 more years for the signal to travel back to Earth, and we might get pictures of Proxima b within a human lifetime. But the engineering challenges are enormous. You need lasers with the power output of 100 nuclear reactors. You need spacecraft weighing just a few grams. You need to solve problems with dust impacts, course corrections, deceleration. Nothing about it is simple. Still, it's theoretically possible, and 20 years is better than 6,800. Sirius, the brightest star in Earth's night sky, is 8.6 light-years away. It's actually a binary system. Sirius A is a bright, hot, white star, about twice the Sun's mass and 25 times brighter. Sirius B is a white dwarf, a dead star that's exhausted its nuclear fuel and collapsed to about Earth's size, despite having roughly the Sun's mass. White dwarfs are dense beyond comprehension. A teaspoon of white dwarf material would weigh about 5 tons on Earth. The star's gravity is so strong that atoms are crushed together, with electrons stripped from their nuclei and packed into the smallest possible space. Sirius B is invisible to the naked eye despite being so close to Earth. It's simply too dim, but it's there, orbiting Sirius A every 50 years, locked in a gravitational dance with its brighter companion. When you look at Sirius tonight, assuming it's visible from your location, you're seeing light that left that star 8.6 years ago. You're seeing the past. If Sirius exploded into a supernova right now, you wouldn't know for 8.6 years. The light from the explosion would travel across those light years of space, taking 8.6 years to reach you. This is one of the strange things about looking at the night sky. You're looking back in time. Every star you see is showing you its past, not its present. The farther the star, the farther back in time you're looking. Within about 30 light years of the Sun, there are maybe 400 stars. Most are red dwarfs, small dim stars like Proxima Centauri. Only about 30 are bright enough to see with the naked eye. This region, sometimes called the local bubble, is where our solar system currently resides. It's a region of space that's slightly less dense than average, with slightly higher temperatures. We happen to drift into it about 5 million years ago, as the Sun orbits the galaxy. The stars in this region aren't permanently our neighbors. Stars are moving. The Sun is moving. Proxima Centauri is moving. In a few thousand years, the nearest star won't be Proxima Centauri anymore. Some other star will have drifted closer. In about 1.3 million years, a star called Gliese 710 will pass within about 10,000 astronomical units of the Sun. Close enough that it might disrupt the Oort cloud, sending comets streaming into the inner solar system. Earth would see a comet shower lasting thousands of years. That's the future. In the past, about 70,000 years ago, a red dwarf called Schultz's star passed within about 50,000 astronomical units of the Sun. Closer than Gliese 710 will come. It probably disturbed some Oort cloud objects, sending them on long, slow journeys toward the Sun. Some of those comets might arrive in the inner solar system thousands of years from now. Stars are not fixed in space. They're moving, orbiting the galaxy, passing each other at different distances. The night sky you see tonight is different from the night sky ancient astronomers saw. Not dramatically different over a human lifetime, but measurably different over thousands of years. The fastest moving star in the sky, from our perspective, is Barnard's star. It's about 6 light-years away and moving toward us at about 140 kilometers per second. It's moving so fast that in about 10,000 years, it will be the closest star to the Sun, overtaking Proxima Centauri. Barnard's star is another red dwarf, slightly larger than Proxima Centauri, but still much smaller than the Sun. It's about 10 billion years old, making it one of the oldest stars in the neighborhood. It probably formed from the first generations of star-forming clouds in our region of the galaxy. These nearby stars, the ones within 30 light-years or so, are the ones we can study in detail. We can measure their masses, their temperatures, their compositions. We can detect planets around some of them. We can track their movements across the sky. But 30 light-years is still a tiny region, a bubble of space that represents a minuscule fraction of the galaxy. And yet, it contains hundreds of stars, maybe thousands if you count the brown dwarfs, the failed stars too small to sustain hydrogen fusion. Let's expand our view. Let's move out to 100 light-years. At this distance, we're looking at thousands of stars. Most are still too dim to see with the naked eye. Red dwarfs dominate the census. But there are some bright stars here too. Arcturus, about 37 light-years away. Vega, about 25 light-years. Altair, Fomalhaut, others. These are the stars that form familiar constellations. The bright points that ancient astronomers used to navigate, to mark the seasons, to tell their myths. But now we can see patterns that weren't visible when we were closer. We can see that stars aren't randomly distributed. There are clusters, young stars that form together and haven't yet drifted apart. There are associations, loose groupings of stars moving through space together. The Hyades, about 150 light-years away, is a cluster of a few hundred stars. The Pleiades, about 440 light-years away, is younger, a group of hot blue stars still surrounded by remnants of the gas cloud they formed from. These clusters tell us something important. Stars don't form in isolation. They form in groups, dozens or hundreds at a time, when giant clouds of gas and dust collapse under their own gravity. The cloud fragments into many clumps, each one becoming a star. Over time, these sibling stars drift apart. Gravity from the rest of the galaxy pulls them in different directions. The cluster dissolves, and the stars go their separate ways, orbiting the galaxy independently. The Sun probably formed in a cluster 4.6 billion years ago, but its siblings have long since scattered. They're somewhere in the galaxy now, indistinguishable from any other star, no longer recognizable as related to the Sun. At 100 light-years, we're also starting to see structure. Not just individual stars, but the beginning of larger patterns. We're inside something called the Orion Arm, or sometimes the Orion Spur. It's a minor spiral arm of the galaxy, a concentration of gas, dust, and young stars stretching for thousands of light-years. From inside, it's hard to map. We can see that there's more gas and dust in certain directions. We can see clusters of young stars, but we can't step outside and look at it from a distance. We're embedded in it, trying to understand the structure from inside. It's like being in a forest and trying to figure out the shape of the forest. You can see the trees around you. You can notice that there are more trees in some directions than others, but you can't see the whole forest at once. Still, by carefully mapping where young stars are, where gas clouds are, where star-forming regions are, astronomers have pieced together a rough picture. The Orion Arm is maybe 10,000 light-years long and a few thousand light-years wide. It's oriented at an angle to the major spiral arms, which is why it's sometimes called a spur rather than an arm. It might be a piece connecting two larger arms, or it might be a separate structure. The Sun is located on the inner edge of this arm, about 26,000 light-years from the galactic center. We're in a relatively clear region, not deep in the dense star-forming areas, but not out in the emptiness between arms either. This location matters. It's part of why Earth exists, why life developed here. If we were closer to the galactic center in the dense regions near the core, radiation levels would be higher. Supernovae would be more frequent. Close encounters between stars might disrupt planetary orbits. If we were farther out in the outer reaches of the galaxy, there might not be enough heavy elements. Carbon, oxygen, nitrogen, iron, all the elements necessary for rocky planets and life, are made in stars. They're scattered through space when stars die. Regions that haven't had many generations of stars don't have much of these elements. We're at the right distance, in a quiet region, but not too quiet. Enough stellar activity to enrich the gas with heavy elements, but not so much that it's dangerous. The Orion Nebula, about 1,300 light-years away, is the nearest major star-forming region. It's visible to the naked eye as a fuzzy patch in Orion's sword, hanging below the 3 stars of Orion's belt. Through a telescope, the Orion Nebula is spectacular. A glowing cloud of gas and dust about 24 light-years across, lit up by young, hot stars at its center. These stars are only about 1 million years old, infants on cosmic timescales. The nebula is a stellar nursery. Gas clouds are collapsing under their own gravity right now, forming new stars. Some of those stars have protoplanetary disks around them, spinning rings of dust and gas that might someday become planets. Watching the Orion Nebula is like watching the process that created our solar system. It's happening now, 1,300 light-years away. Of course, what we see is 1,300 years out of date. The nebula, as it is right now, in this moment, we won't see for another 1,300 years. But that's a blink of an eye for stellar timescales. The stars forming there will live for millions or billions of years. Some of the massive ones, the bright blue giants, will only last a few million years before exploding as supernovae. But the smaller ones, the sun-like stars and red dwarfs, will burn for billions of years. Perhaps planets are forming around those stars right now. Perhaps in a few billion years, life will evolve on one of those worlds. Perhaps someday, beings on a planet orbiting a star in the Orion Nebula will look up at their night sky and wonder about the stars they see. Further out in the Orion Arm are other stellar nurseries. The Eagle Nebula, about 7,000 light-years away, famous for the pillars of creation image taken by the Hubble Space Telescope. Towering columns of gas and dust, light-years tall, where new stars are being born. The Carina Nebula, about 8,500 light-years away, home to some of the most massive stars known. Eta Carinae, a star perhaps 100 times the Sun's mass, so massive and unstable that it might explode as a supernova at any time. When it does, it will briefly be the brightest star in Earth's sky, visible even during daytime. These are the landmarks of the Orion Arm. The bright regions, the places where stars are actively forming, where the galaxy is creating new suns that will shine for millions or billions of years. Between these bright regions, there's a lot of emptiness. Gas clouds that haven't yet collapsed, older stars drifting through space, dark regions where dust blocks the light from stars behind it. From 1,000 light-years away, if you could somehow step outside and look back, you'd see the Orion Arm as a faint arc of light, a concentration of blue-white stars, young and hot, surrounded by glowing nebulae. The sun would be lost among millions of other yellow stars, too faint and ordinary to notice. At 10,000 light-years, you'd see the Orion Arm as one feature among several. Other arms would be visible, curving through space, each one a concentration of stars and gas. This is where we start to see the galaxy's structure, the spiral pattern that defines what the Milky Way is. But we're getting ahead of ourselves again. We're trying to see the whole forest when we're still among the trees. Let's stay focused on our journey outward. Let's keep expanding our view, light year by light year, until the galaxy's structure becomes clear. Because right now, at distances of a few thousand light years, we're seeing pieces, fragments. We see our arm, hints of other arms, but not the whole picture. The stars around us are moving, not randomly, but with purpose. They're all orbiting the galactic center, just like the sun is. Stars closer to the center orbit faster. Stars farther out orbit slower. It's similar to how planets orbit the sun, with Mercury racing around in 88 days, while Neptune takes 165 years. The sun takes about 225 million years to complete one orbit around the galaxy. This is sometimes called a galactic year or cosmic year. Since the sun formed 4.6 billion years ago, it's completed about 20 orbits. The last time the sun was in this position in its orbit, dinosaurs walked the Earth. The time before that, the supercontinent Pangaea was forming. The time before that, life was still mostly microbial, confined to the oceans. We're moving through space at about 220 kilometers per second as we orbit the galaxy. That's fast. Fast enough to cross the United States in about 20 seconds. But because the galaxy is so large, this speed feels slow. It takes 225 million years to complete one lap. Other stars are moving at different speeds. Some are moving in the same general direction as the sun, fellow travelers on similar orbits. Others are moving differently, on more elliptical orbits, swooping closer to the galactic center and then back out. Over millions of years, the neighborhood changes. Stars that are nearby now won't be nearby forever. New stars will drift into our region. Old neighbors will drift away. The constellations we see tonight are temporary. Over tens of thousands of years, they'll slowly distort as stars move at different speeds in different directions. The Big Dipper will stop looking like a dipper. Orion's belt will no longer be 3 stars in a row. This is cosmic time, time on scales that dwarf human civilization. But it's real motion, real change, happening constantly. As we continue expanding our view, reaching distances of tens of thousands of light years, we start to see the bigger picture. The Orion Arm we've been exploring is just one part of a larger structure. A minor arm, really. A relatively small feature in the grand scheme of the galaxy. The major arms are elsewhere, larger, more prominent, containing more stars and gas. The Perseus Arm lying farther from the galactic center than we are. The Scutum Centaurus Arm, closer to the center. These are the grand spirals, the prominent features that define the galaxy's structure. Between these major arms lie the minor arms, Sagittarius, Norma, and our own Orion Arm. Smaller concentrations, sometimes just bridges of gas and young stars connecting the major arms. From our position, about 26,000 light-years from the galactic center, we're sitting between Perseus and Scutum Centaurus, in a relatively quiet spot. Not in the dense star-forming regions of a major arm, not in the empty space between arms, but in a minor arm, a middle ground. This position, this location in the galaxy, is part of what's sometimes called the galactic habitable zone. The idea is that there are regions of the galaxy where conditions are more favorable for life. Too close to the center and there's too much radiation. Too many supernovae. Too many close stellar encounters that could disrupt planetary orbits. Too much chaos. Too far from the center and there aren't enough heavy elements. The outer regions of the galaxy haven't had as many generations of stars, so there's less carbon, oxygen, iron, all the elements planets and life need. And then there's the spiral arm question. Major spiral arms are sites of intense star formation. Massive stars form there, burn bright, and explode within a few million years. If a solar system was in a major arm during these fireworks, the radiation from nearby supernova might strip away planetary atmospheres, sterilize surfaces, prevent life from gaining a foothold. Our location in a minor arm between the major arms, at a moderate distance from the center, might be ideal. Enough heavy elements to form rocky planets. Not so much activity that it's dangerous. A quiet neighborhood where life can develop undisturbed for billions of years. This might be why we're here. Why Earth exists, why life evolved, why you're reading this now. Because the solar system happened to form in the right place. Or maybe not. Maybe this is just circumstance. Maybe life can arise anywhere under all sorts of conditions, and we only think our location is special because it's where we are. We don't know. We don't have enough data. We've only found life in one place, on one planet, in one solar system, in one part of one galaxy. Sample size of one. But it's an interesting thought that our address in the galaxy might matter, that being here in this arm at this distance at this time might be part of the story of how we came to exist. The center is not the whole story, though. Beyond the bulge, beyond the spiral arms, beyond the disk altogether, there's more to the Milky Way. A vast spherical halo of stars, and something else. Something invisible that makes up most of the galaxy's mass. But we're getting ahead again. We've reached the heart of the galaxy. We've seen the black hole. Now we need to understand what lies beyond the bright regions, beyond the stars and gas we can easily see. Because the Milky Way is more than just its visible parts. Much more. The spiral arms aren't solid objects. This is important to understand. They're not like the arms of a pinwheel, rigid structures that spin around the center. If they were, they'd wrap tighter and tighter over time, winding up like rope around a spool. After a few rotations, maybe 10 or 20 galactic years, the spiral structure would have wound itself into a tight coil and disappeared. But the Milky Way is old. It's been rotating for billions of years, hundreds of galactic rotations, and yet the spiral arms persist. They're still there, still distinct, still tracing elegant curves through space. The reason is that spiral arms are density waves, not matter. Waves. Think of traffic on a highway. Cars move along at roughly constant speed, but sometimes traffic jams form. The jam is a region of higher density. More cars per mile. The jam moves along the highway at its own speed, often slower than the cars themselves. A car enters the jam from behind, slows down, then speeds up again as it exits the front of the jam. The car passes through the traffic jam. The jam itself, the region of high density, persists even though the individual cars are constantly changing. Spiral arms work the same way. They're regions where stars and gas are temporarily bunched together. The stars orbit the galaxy at their own speeds, but as they pass through a spiral arm, they slow down slightly, bunch up, then speed up again as they exit. The arm persists even though the stars passing through it are constantly changing. This bunching creates conditions for star formation. When gas clouds enter a spiral arm, they get compressed. The density wave squeezes them. And sometimes this compression is enough to trigger gravitational collapse. The cloud fragments. Pieces of it start falling inward under their own gravity. New stars begin to form. The most massive stars, the bright blue giants, are born in these compressed regions. They shine brilliantly, outshining the sun by factors of thousands or millions. But they don't live long. A few million years, maybe 10 million at most, before they exhaust their fuel and explode as supernovae. Because they live such short lives, these massive stars barely have time to move away from where they were born. They light up the spiral arms, marking the regions of active star formation. Then they die, still within the arm, their explosions enriching the surrounding gas with heavy elements. This is why spiral arms look bright. They're not more massive than the space between arms. They don't contain significantly more total matter, but they contain more young, bright stars. Stars that are actively forming or recently formed. Stars that are hot and luminous, pouring out light at prodigious rates. Between the arms there are still plenty of stars, but they're older, cooler, dimmer. Yellow stars like the sun, red dwarfs, white dwarfs slowly cooling. Stars that have drifted away from their birthplaces over millions or billions of years. The Orion arm where we live is sometimes called a spur because it's not one of the major arms. It's a smaller feature, maybe a bridge connecting two larger arms, maybe just a local enhancement in the density wave pattern. Astronomers aren't entirely certain of its nature because mapping the Milky Way's structure from inside is difficult. But the major arms are clear. Perseus, lying farther from the galactic center than we are. Scutum Centaurus, closer to the center. Sagittarius and Norma, the other minor arms. These arms don't stay in fixed positions. They're rotating, but at a different speed than the stars. The pattern rotates slower than most stars' orbit. This is why stars pass through the arms instead of staying within them. Our sun probably passes through a spiral arm roughly every 100 million years or so. We're between arms now, in a relatively clear region. Safer, perhaps. Less radiation from nearby supernovae. Less disturbance from the violent processes happening in star-forming regions. Some astronomers think this matters for life, that being between arms provides a more stable environment. Fewer supernovae means less chance of a nearby explosion bathing Earth in harmful radiation. Fewer massive stars means less disruption to the Oort cloud. Fewer comets shaken loose and sent hurtling toward the inner solar system. Maybe, or maybe life is more resilient than we think. Maybe it can arise and thrive even in the chaotic environment of a spiral arm. We don't know. We only have one example to study. From above, if you could somehow rise above the galactic plane and look down, the Milky Way would be stunning. A grand spiral, arms curving gracefully outward from the center, traced in the blue-white light of young stars and the reddish glow of ionized gas. Between the arms, darker regions, still containing billions of stars but appearing dim by comparison. The whole structure would be about 100,000 light-years across, maybe 105,000. Measurements vary depending on how you define the edge. The disk is flat, only about 1,000 light-years thick in most places, a ratio of about 100 to 1. If you scaled the Milky Way down so the disk was as thick as a sheet of paper, it would be about 30 feet across. And we're embedded in this disk, 26,000 light-years from the center, unable to rise above it and see it from outside. We're like ants crawling on a dinner plate, trying to figure out the plate's shape and size from our limited perspective. We can measure distances to nearby stars. We can map the distribution of gas and dust. We can trace the arms to some extent, but we can't step back and see the whole picture the way we can see Andromeda. Still, bit by bit, measurement by measurement, we've built up a map. Not perfect, but getting better. We know the major arms. We know their approximate positions. We know where star-forming regions are, where dense molecular clouds lie, where the bright young stars cluster. Radio telescopes have been particularly useful for this. They can detect the 21-centimeter emission from neutral hydrogen, mapping where gas is concentrated. They're not blocked by dust the way optical telescopes are, so they can see through the murky regions that hide parts of the galaxy from visible light. Infrared telescopes also help. They detect warm dust, the kind that glows from heat rather than reflected starlight. Young stars heat their surroundings, making dust warm enough to glow in infrared. By mapping infrared emission, we can find star-forming regions even when they're hidden behind layers of dust. The picture that emerges is one of a galaxy in constant, slow motion. Gas drifting through the spiral arms, stars being born in the dense regions, young stars lighting up their surroundings, older stars drifting out of the arms, continuing their orbits around the galactic center. Everything rotating, but not uniformly, not like a solid wheel. Stars closer to the center orbit faster. Stars farther out orbit slower. This is similar to how planets orbit the Sun. Mercury races around in 88 days. Neptune takes 165 years. The inner regions move faster because the gravitational pull is stronger there. Near the galactic center, maybe 3,000 light-years from the core, stars complete an orbit in just 10 million years. Out where we are, 26,000 light-years from the center, it takes 225 million years. In the outer regions, 50,000 light-years from the center, an orbit might take 500 million years. This differential rotation, different speeds at different distances, is part of what maintains the spiral structure. It's also part of what creates it. Density waves arise partly because of this differential rotation, arising from instabilities in the disk that amplify into spiral patterns. But all of this, the spiral arms, the orbiting stars, the gas clouds and star formation, all of it revolves around something at the center, something that dominates the inner galaxy through its sheer mass and gravitational influence. The galactic bulge. As you move inward from our position, toward the center of the galaxy, things change. Star density increases. Dust thickens. The environment becomes more crowded, more chaotic. The bulge is a roughly spherical concentration of stars at the galaxy's heart. about 10,000 light-years across, maybe 15,000, depending on how you measure it. It's not a perfect sphere. It's slightly elongated, bar-shaped actually, which is why the Milky Way is classified as a barred spiral galaxy. This central bar is made of stars, billions of them, orbiting in elongated paths that trace out a bar-like structure. From above, if you could see the galaxy from outside, you'd notice that the inner regions don't have a circular symmetry. They're stretched out, forming a bar maybe 20,000 light-years long and half as wide. Bars are common in spiral galaxies. About 2/3 of all spirals have them. They arise from instabilities in the disk. Under certain conditions, orbits in the inner galaxy arrange themselves into this elongated pattern. Once formed, bars are stable, lasting billions of years. They have effects on the galaxy's evolution. Bars can funnel gas inward, toward the very center, feeding the supermassive black hole. They can also influence where spiral arms form, creating resonances at certain distances where gas piles up and star formation intensifies. The bulge is old. Most of the stars here formed billions of years ago when the galaxy was young. They're population 2 stars, made from gas that hadn't yet been enriched with heavy elements from earlier generations of supernovae. Lower metallicity, as astronomers say. Less iron, less carbon, less oxygen. These stars have a reddish tint. They're cooler than the hot blue stars of the spiral arms. Many are red giants, stars that have exhausted the hydrogen in their cores and swollen to enormous sizes. Some of these giants are larger than Earth's orbit around the Sun. Huge, bloated stars in the final stages of their lives, slowly puffing their outer layers into space. The density of stars in the bulge is extraordinary. If you lived on a planet near the galactic center, your night sky would be spectacular. Thousands of stars bright enough to cast shadows. No true darkness at night, just a perpetual twilight from the combined glow of countless suns. The nearest star to you might be only a light year away, maybe less. Compare that to our neighborhood, where the nearest star is over 4 light years distant. In such a crowded environment, close encounters between stars become possible. Not collisions. Stars are still too small and too far apart for actual collisions, but gravitational encounters. One star passing within a few thousand astronomical units of another, close enough for their gravitational fields to perturb each other's orbits. Binary star systems can be disrupted. A close encounter with a third star might rip the binary apart, sending one star flying off at high speed while the other is captured into a new binary with the intruder. Planetary systems might be disturbed. A close stellar encounter could fling planets out of their orbits, sending them careening into interstellar space, or dropping them into their star. And then there's the radiation. More supernovae happen in the central regions because there are more stars. More massive stars being born, living brief lives, and exploding. The rate of supernovae in the bulge is perhaps 10 times higher than in our region of the galaxy. Each supernova floods the surrounding space with high-energy particles and radiation. If you were living on a planet in the bulge, you'd need substantial magnetic fields and thick atmosphere to protect against this radiation. Life would face challenges we don't encounter in our quieter neighborhood. This is part of why the galactic habitable zone concept exists. The idea that there are regions of the galaxy more conducive to life than others. too close to the center and the environment is too harsh. Too many supernovae, too much radiation, too many stellar encounters disrupting planetary systems. Too far from the center, and there might not be enough heavy elements. Rocky planets need iron, silicon, magnesium. Life, at least as we know it, needs carbon, oxygen, nitrogen, phosphorus. These elements are made in stars and scattered by supernovae. Regions that haven't had many generations of stars don't have much of them. We're in the middle, a sweet spot. Enough heavy elements for rocky planets and life. Not so much activity that it's dangerous. But this is speculative. We don't know if life requires this kind of environment. Maybe life is more adaptable. Maybe it can arise in the harsh radiation of the galactic center, or in the element-poor outer reaches. Until we find life elsewhere, we're just guessing, based on the one example we have. The bulge isn't uniform. There are streams of stars, remnants of smaller galaxies that merged with the Milky Way billions of years ago. Gravitational archaeology, astronomers call it. Looking at the distribution and motion of stars to reconstruct the galaxy's history. Computer simulations show that galaxies grow through mergers. Small galaxies collide and combine, forming larger galaxies. The Milky Way has likely absorbed dozens of smaller galaxies over its history. Most of those satellite galaxies have been completely torn apart, their stars scattered throughout the bulge and halo. But we can still see traces. Groups of stars with unusual orbits moving in ways that suggest they didn't form here. Streams of stars stretching across the sky, the remnants of a dwarf galaxy that wandered too close and was ripped apart by tidal forces. The Sagittarius dwarf elliptical galaxy is currently being torn apart. It's on the opposite side of the Milky Way from us, about 70,000 light-years away. Streams of its stars wrap around the galaxy multiple times. This little galaxy, containing only a few tens of millions of stars, is being pulled apart by the Milky Way's gravity. Its stars are being added to the Milky Way's halo and bulge. Eventually, in a few 100 million years, the Sagittarius dwarf will be gone completely, dissolved. Its stars scattered and mixed with ours, no longer identifiable as having come from a separate galaxy. This is how large galaxies grow, by consuming smaller ones. At the very heart of the bulge, at the exact center of the Milky Way, lies something remarkable. Something that was once theoretical, suspected but not confirmed until recent decades provided proof. Sagittarius A star, the supermassive black hole at the center of our galaxy. It's about 26,000 light-years away from us. Located in the constellation Sagittarius, when viewed from Earth. The asterisk in its name denotes it as an interesting radio source. Astronomers have been detecting radio waves from this region since the 1970s. Strong emission from the galactic center. But they didn't know what was producing it. We can't see the galactic center in visible light. Too much dust in the way. The light from stars near the center is absorbed and scattered by thick clouds of interstellar dust lying between us and it. If you could remove all the dust, the galactic center would be one of the brightest regions in the night sky. But the dust blocks it, hiding it from optical telescopes. Radio waves, however, pass through dust. So do X-rays and infrared. Using these wavelengths, astronomers could study the galactic center despite the obscuring dust. What they found was intriguing. A compact source of radio emission, fluctuating X-ray emissions, And stars, dozens of stars, orbiting something they couldn't see. These stars were the key. By tracking their motion over years and decades, astronomers could measure the mass of whatever they were orbiting. And the answer was stunning. There's something at the galactic center with a mass of about 4.3 million times the Sun's mass. That's 4.3 million solar masses, compressed into a region smaller than the solar system. Nothing else could be that massive and that compact. Not a cluster of stars, not a cloud of dark matter. Only a black hole could have that much mass in that small A volume. A black hole, remember, is a region of space where gravity is so strong that nothing can escape, not even light. It forms when massive amounts of matter collapse to a point, creating infinite density at the center and warping space-time around it so severely that anything crossing the event horizon, the boundary around the black hole, can never return. Supermassive black holes are different from stellar mass black holes. Stellar mass black holes form when massive stars collapse at the end of their lives. They might have masses between 5 and 100 times the Sun's mass. Supermassive black holes are millions or billions of times more massive. We're not entirely sure how they form. They might grow from smaller black holes that merge and accumulate matter over billions of years. Or they might form directly in the early universe from the collapse of enormous gas clouds. The details are still being worked out, but we know they exist. Nearly every large galaxy has one at its center. Andromeda has one about 100 million solar masses. Messier 87, a giant elliptical galaxy, has one of about 6.5 billion solar masses. The Milky Way's is relatively modest by comparison, just 4.3 million solar masses. Despite its enormous mass, Sagittarius A star is physically small. The event horizon, the boundary beyond which nothing can escape, is only about 12 million kilometers across, about 17 times the Sun's diameter. Light takes about 40 seconds to cross it. That's incredibly small for something so massive. If you could somehow compress the Earth to black hole density, it would be about 9 millimeters across. A marble. The Sun, compressed to a black hole, would be about 3 kilometers across. Sagittarius. A star's event horizon is small enough that it would fit comfortably inside Mercury's orbit. The entire black hole, the most massive object in the galaxy, occupies a space smaller than the innermost region of the solar system. We can't see the black hole directly. By definition, it emits no light, but we can see its effects. The Event Horizon Telescope, a network of radio telescopes spanning the globe working together, captured an image of Sagittarius A star in 2022. The image shows a dark circle, the black hole's shadow, surrounded by a bright ring. The ring is emission from hot gas orbiting the black hole at tremendous speeds, approaching the speed of light. This gas is heated to millions of degrees by friction and compression as it spirals inward. It glows brightly in radio waves and X-rays. The dark circle in the center is larger than the event horizon. It's the photon sphere, the region where light can orbit the black hole. Light emitted from the glowing gas on the near side of the black hole can curve around the black hole's extreme gravity and come toward us, creating the bright ring we see. The shadow is about 52 microarc seconds across, as seen from Earth. To give you a sense of how small that is, imagine a donut on the moon. If you were on Earth looking at the moon, that donut would appear about 52 micro-arc seconds across. The Event Horizon Telescope can resolve features that small. This was an incredible achievement. Coordinating radio telescopes around the world, synchronizing their observations to nanosecond precision, combining their data to create an image with resolution finer than anything a single telescope could achieve. The image confirmed predictions from general relativity. The size and shape of the shadow matched what Einstein's equations predicted for a black hole of this mass. It's one of the most extreme tests of general relativity ever performed, and the theory passed with flying colors. Sagittarius, a star, is relatively quiet. It's not actively consuming large amounts of matter right now. If it were, the galactic center would be far brighter. The black hole would be glowing intensely as matter fell into it, heated to incredible temperatures by the compression and friction of the accretion process. Some galaxies have active galactic nuclei, where the central black hole is gorging on gas and stars. These active nuclei can outshine the entire rest of the galaxy. Jets of particles shoot out perpendicular to the accretion disk at nearly the speed of light, extending for thousands of light years into space. These are among the most energetic phenomena in the universe. The Milky Way's black hole isn't doing this. It's dormant, or at least dozing. It occasionally flares up when gas or an unlucky star gets too close and falls in. Astronomers see these flares as sudden brightenings in X-rays or infrared. But most of the time, Sagittarius A star is quiet. This is probably good for us. An active galactic nucleus would flood the inner galaxy with radiation. Not immediately dangerous at our distance, 26,000 light-years away, but potentially harmful over long timescales. Stars orbit Sagittarius A star just like planets orbit the Sun. Dozens of stars have been tracked, their orbits measured precisely. Some of these stars pass within about 120 astronomical units of the black hole, closer than the distance from the Sun to Voyager 1. At that distance, they're moving at about 5,000 kilometers per second, about 2% of the speed of light, fast enough to cross the distance from Earth to the Moon in less than 2 minutes. These stars experience extreme gravitational effects. Time dilation, for instance. Time runs slower in strong gravitational fields, an effect predicted by general relativity. For a star passing close to Sagittarius A star, time is running measurably slower than for us. If the star had a clock, that clock would tick slightly slower than a clock on Earth. The difference is small, but measurable with precise instruments. The orbits themselves are influenced by relativity. They precess, meaning they don't close perfectly. Each orbit, the star's path shifts slightly. This precession has been measured and matches the predictions of general relativity to high precision. Watching these stars orbit an invisible object is one of the strongest pieces of evidence for Sagittarius A star being a black hole. Nothing else could be that massive in that small A volume. The star's orbits demonstrate that there's something there, and the only plausible explanation is a supermassive black hole. The region around Sagittarius A star is chaotic. Gas clouds swirl in complex orbits. Some are being heated and torn apart by tidal forces. Others are feeding the black hole, spiraling inward slowly, taking thousands of years to cross the event horizon. Occasionally, a star wanders too close. the black hole's tidal forces, the difference in gravitational pull between the star's near side and far side, becomes strong enough to overcome the star's own gravity. The star is stretched into a long strand, spaghettified. The near side is pulled harder than the far side, and the star is ripped apart. This produces a tidal disruption event. The stellar material streams towards the black hole, forms an accretion disk, heats up, and emits intense radiation for weeks or months before settling down again. These events have been observed in other galaxies. They produce distinctive X-ray and optical signatures that astronomers can detect. Sagittarius A star has probably disrupted hundreds or thousands of stars over its lifetime, each one adding mass to the black hole, making it slightly larger, slightly more powerful. Black holes grow by consuming matter. Gas, dust, stars. Anything that crosses the event horizon adds to the black hole's mass. Sagittarius A star has been growing for billions of years, possibly since the early days of the galaxy's formation. It might have started as a smaller black hole, maybe a few hundred or thousand solar masses, formed from the collapse of massive gas clouds in the early universe. Then it grew by merging with other black holes and by accreting matter from its surroundings. Over billions of years consuming stars and gas clouds, merging with smaller black holes from galaxies that fell into the Milky Way, it grew to its current size of 4.3 million solar masses. And it's still growing, slowly. The amount of matter it's consuming now is small, maybe equivalent to a few Earth masses per year. At that rate, it would take billions of years to grow significantly larger. But if a large gas cloud or a star cluster fell into the central region, it could gorge itself, growing much faster. Active phases might alternate with quiet phases over the galaxy's history. The black hole spins. All rotating objects have angular momentum, and when matter falls into a black hole, it carries angular momentum with it. The black hole starts spinning faster. Sagittarius A star is rotating at a significant fraction of the maximum possible speed for a black hole. Maybe 90% of the theoretical limit. This rotation drags space-time around the black hole, a phenomenon called frame dragging. Near the event horizon, space-time itself is being pulled around in the direction of the black hole's rotation. This creates strange effects. Light emitted near the black hole is twisted and distorted by the rotating space-time. Orbits close to the black hole are influenced not just by the black hole's mass, but by its spin. The faster the black hole spins, the more extreme these effects become. Studying Sagittarius, A star teaches us about gravity in its most extreme form, about how space-time behaves when it's warped beyond anything we can replicate on Earth or in laboratories, about how matter behaves in the strongest gravitational fields in the universe. It also raises questions we cannot yet answer. What happens at the center of a black hole? General relativity predicts a singularity, a point of infinite density, where the laws of physics break down. But we do not know if this is real, or if quantum effects prevent true singularities from forming. Does information that falls into a black hole get destroyed, or is it somehow preserved? This is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Could there be something other than a singularity at the center? Maybe quantum gravity, a theory that unifies quantum mechanics and general relativity, would reveal something different. We do not have that theory yet, so we do not know. What we do know is that Sagittarius A star is there, at the heart of our galaxy, governing the motions of millions of nearby stars through its immense gravity. Silent now, but capable of violent outbursts, growing slowly, accumulating mass over eons. It has been there since the early days of the Milky Way. It will be there long after the sun dies. Long after Earth is gone. Long after the last stars form in the galaxy. Eventually, in the far future, trillions of years from now, the Milky Way will run out of gas. Star formation will cease. The galaxy will grow darker as stars exhaust their fuel and die. Sagittarius. A star will still be there, orbited by the remnants of dead stars. White dwarfs, neutron stars, black holes. A graveyard slowly spiraling into the central black hole. But that is the distant future. For now, Sagittarius, a star, sits at the center of a thriving galaxy. A galaxy still forming stars, still evolving, still changing. And we, 26,000 light-years away, orbit around it, completing one circuit every 225 million years, unaware in our daily lives that we are bound to this invisible monster at the galaxy's heart. The center is not the whole story, though. Beyond the bulge, beyond the spiral arms, beyond the disk altogether, there is more to the Milky Way. A vast spherical halo of stars and something else, something invisible that makes up most of the galaxy's mass. But we are getting ahead again. We have reached the heart of the galaxy. We have seen the black hole. Now we need to understand what lies beyond the bright regions, beyond the stars and gas we can easily see. Because the Milky Way is more than just its visible parts. Much more. Beyond the disk, beyond the bright spiral arms and the crowded bulge, there is another realm. A spherical region surrounding the entire galaxy. Faint, diffuse, and ancient. The stellar halo. If you could somehow rise above the Milky Way's disk and look down at it from 1,000,000 light-years away, you would see the bright spiral clearly. The arms, the bulge, the disk glowing with the light of hundreds of billions of stars. But surrounding all of it, extending far beyond the visible structure, you would notice a faint glow. A spherical distribution of stars, much dimmer than the disk, spread out over a vast volume. This is the halo. And it tells a different story than the disk does. The halo extends perhaps 130,000 light-years from the galactic center. Maybe farther. It's hard to define exactly where it ends because the star density gradually fades with distance. There's no sharp boundary, just stars getting sparser and sparser until they're indistinguishable from the general background. The stars in the halo are old, very old. Population 2 stars formed over 12 billion years ago when the universe was young and the Milky Way was just beginning to take shape. These stars have different compositions than sun-like stars in the disk. They're metal poor in astronomical terms. Less iron, less carbon, less oxygen, more hydrogen and helium, the primordial elements left over from the Big Bang. This makes sense when you think about the history. The first stars that formed in the universe had nothing but hydrogen and helium to work with. No heavy elements existed yet. Those elements had to be created in stellar cores, through nuclear fusion, and then scattered into space when those stars died. So the earlier stars were pure hydrogen and helium. They lived, fused lighter elements into heavier ones, and died. Some exploded as supernovae, blasting their enriched material into space. That material mixed with the pristine hydrogen and helium, creating gas clouds with small amounts of heavy elements. The next generation of stars formed from that slightly enriched gas. They had more heavy elements than the first generation, but still far less than stars forming today. The halo stars are from these early generations. They formed when the galaxy was young, before most of the heavy element enrichment happened. Their chemistry is a fossil record, preserving information about conditions in the early universe. Their orbits are different too. While disk stars orbit in roughly circular paths around the galactic center, staying close to the disk plane, halo stars follow highly elliptical orbits. They swoop down through the disk, pass near the galactic center, then climb back out into the halo on the other side. Some halo stars spend most of their time tens of thousands of light years above or below the disk, only briefly passing through during their long orbits. Their orbital periods might be hundreds of millions of years. This difference in orbits tells us something about how these stars formed. The disk formed from gas that collapsed into a rotating plane. Conservation of angular momentum ensured that the gas settled into a flat structure. Stars forming in that disk inherited the rotation. But the halo stars formed differently. They probably formed in small clumps, mini-galaxies that fell together to build the early Milky Way. Each clump had its own angular momentum, its own direction of rotation. When they merged, their stars were scattered onto random orbits, not aligned with the disk. Some of these merger events happened recently enough that we can still see their remnants. Streams of stars stretched across the sky, marking the paths of dwarf galaxies that were torn apart by the Milky Way's gravity. The Sagittarius dwarf elliptical galaxy mentioned earlier is being ripped apart right now. Streams of its stars wrap around the Milky Way multiple times, like ribbons. Eventually, those stars will be completely mixed into the halo, and we'll lose track of which stars came from Sagittarius and which came from other mergers. But for now, we can trace them. We can identify stars that share similar orbits, similar compositions, similar ages. These are siblings, born in the same dwarf galaxy, now scattered across the halo as that galaxy dissolves. This is galactic archaeology, using the properties and motions of stars to reconstruct the Milky Way's history, to figure out which smaller galaxies merged with us, when they merged, how massive they were. It's a bit like trying to reconstruct a shattered vase from the pieces, except the pieces are stars, scattered across hundreds of thousands of light years, and the vase was broken billions of years ago. Despite the challenges, astronomers have made progress. They've identified several ancient merger events. The Gaia-Enceladus merger, which happened about 10 billion years ago, brought in a dwarf galaxy with perhaps 5% of the Milky Way's current mass. Many of the halo stars today probably came from that merger. There have been others, smaller mergers, more recent ones, each one adding stars to the halo, changing the galaxy's structure slightly. This process continues today. The Milky Way is still consuming smaller galaxies. In a few 100 million years, there will be new streams in the halo, new populations of stars mixed in, evidence of the mergers happening now. Embedded within the halo are globular clusters, dense spherical collections of stars, each containing hundreds of thousands or even millions of stars, packed into a region only tens of light years across. The Milky Way has about 150 known globular clusters. There might be more hidden behind dust clouds or on the far side of the galaxy where we can't easily see them. These clusters are spectacular. If you could visit a planet orbiting a star in the core of a globular cluster, your night sky would be filled with thousands of bright stars. Stars so close and so luminous that they'd cast shadows. True darkness would be impossible. The combined starlight would create perpetual twilight. Globular clusters are among the oldest objects in the galaxy. Most formed over 12 billion years ago, possibly even 13 billion years ago, within the first billion years after the Big Bang. They're fossils from the galaxy's youth. Their stars are metal poor, just like the halo stars. They formed from pristine gas before generations of supernovae had enriched the interstellar medium with heavy elements. But there's a puzzle. Globular clusters seem to have multiple stellar populations. All the stars in a cluster are roughly the same age, formed at roughly the same time, but they have slightly different chemical compositions. Some stars have more heavy elements than others despite being the same age. The leading explanation is that star formation in globular clusters happened in multiple waves. The first generation of stars formed, lived for a few million years, and enriched the gas with supernova ejecta. Then a second generation formed from that enriched gas. So you have two populations of the same age, but different compositions. But the details are still being worked out. Globular clusters are more complicated than they initially appeared. They orbit the galaxy on long elliptical paths, just like the halo stars. Some clusters pass through the disk regularly. When they do, they interact with the disk's gravity and gas clouds. These interactions strip away the cluster's outer stars, gradually whittling it down over billions of years. Other clusters orbit farther out, in safer regions where they're not disturbed as often. These clusters remain intact, preserving their original structure. The most massive globular cluster in the Milky Way, Omega Centauri, is unusual. It's so massive, containing several million stars, that some astronomers think it might be the remnant core of a dwarf galaxy that was stripped of its outer stars during a merger. If so, it might even contain an intermediate mass black hole at its center. Globular clusters are also used as standard candles for measuring distances. Because they're so bright, containing hundreds of thousands of luminous stars in a compact region, they can be seen at great distances. Astronomers have used globular clusters to measure distances to other galaxies, helping map the local universe. But perhaps their most important role is as cosmic laboratories. Because all the stars in a globular cluster formed at the same time from the same gas cloud, they provide a controlled experiment. You can study how stars of different masses evolve, all starting from the same conditions. This has taught us a lot about stellar evolution, about how stars age, how they die, what happens when they run out of fuel. Now we need to talk about something we cannot see, something that makes up most of the galaxy's mass, but does not emit any light. Dark matter. The evidence for dark matter comes from studying how things move in the galaxy. Specifically, how fast stars orbit the galactic center at different distances. Newton's laws and general relativity make clear predictions about this. If you know how much mass is inside a star's orbit, you can calculate how fast that star should be moving to maintain a stable orbit. In the solar system, this works perfectly. The planet's orbital speeds match the predictions based on the sun's mass and the distance from the Sun. Mercury orbits fast because it's close to the Sun and feeling strong gravity. Neptune orbits slowly because it's far away and feeling weaker gravity. You would expect the same thing in a galaxy. Stars close to the center should orbit fast. Stars farther out should orbit slower. But that is not what we observe. When astronomers measure the orbital speeds of stars at different distances from the galactic center, they find something strange. The speeds do not decrease with distance the way they should. They stay roughly constant, even far from the center. This is called a flat rotation curve, and it does not make sense based on the visible matter. The only way to explain it is if there is additional mass we are not seeing. Mass distributed in a large halo around the galaxy, extending far beyond the visible stars and gas. This invisible mass is dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all as far as we can tell. But it has mass, and therefore gravity, and it affects the motions of stars and gas. The Milky Way's dark matter halo probably extends 600,000 light-years from the center. Maybe farther. It is hard to measure precisely because there is nothing out there emitting light to trace the dark matter's distribution. We only know it is there from its gravitational effects. The mass of this dark matter halo is enormous, about 10 times the mass of all the stars and gas in the galaxy combined. The Milky Way's total mass, including dark matter, is roughly 1 trillion times the Sun's mass. Most of that is dark matter. Without dark matter, the galaxy would not exist. The stars would fly apart. There would not be enough gravity to hold everything together. Dark matter also played a crucial role in the galaxy's formation. In the early universe before stars formed, dark matter was already there, clumping under its own gravity. These dark matter clumps created gravitational wells, regions where normal matter could fall in and accumulate. Gas fell into these dark matter halos, compressed, heated, fragmented, and eventually formed the first stars. The visible galaxy we see today is built on a dark matter foundation. What is dark matter made of? We don't know. It's one of the biggest mysteries in physics. It can't be normal matter. It can't be made of protons, neutrons, and electrons. We've carefully measured how much normal matter exists in the universe, based on the abundances of elements produced in the Big Bang. There simply isn't enough to account for dark matter, so it must be something else, some exotic particle or particles that interact very weakly with normal matter. Weakly interacting massive particles, or WIMPs, are a popular candidate. Axions are another. Sterile neutrinos, primordial black holes, formed in the early universe. Experiments around the world are searching for these particles. Detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to occasionally collide with an atomic nucleus. Particle colliders trying to create dark matter particles and detect them. So far, nothing conclusive. We know dark matter is there from its gravitational effects, but we haven't directly detected the particles. This might seem frustrating. How can something make up most of the galaxy's mass, and we don't know what it is? But that's science. Sometimes you know something exists before you understand what it is. Dark matter is detectable through gravity. Figuring out its nature is the next step, and it might take decades or even centuries. Still, we've learned a lot. We know dark matter is stable. It doesn't decay quickly, or we'd see the decay products. We know it doesn't interact strongly with light or normal matter, or we'd see those interactions. We know it clumps on galactic scales but doesn't collapse into dense objects like stars, which tells us something about its properties. Every constraint helps narrow down the possibilities. Every failed detection rules out certain models. Slowly, we're closing in on an answer. The dark matter halo is what defines the Milky Way's true size. The visible disk is only 100,000 light-years across, but the dark matter halo extends 6 times farther, making the galaxy's total extent more like 600,000 light-years, or more. From this perspective, the bright spiral we see is just the core, the tip of a much larger structure, most of which is invisible. This is true for all galaxies. Every galaxy we observe, every spiral and elliptical and irregular, is surrounded by a dark matter halo larger than the visible structure. The universe is filled with dark matter. Most of the matter that exists is this mysterious substance we cannot see directly. It is humbling. The stuff we are made of, protons, neutrons, electrons, atoms, molecules, makes up only about 15% of the matter in the universe. The other 85% is something else entirely. And it is not just matter. Most of the universe's total energy density is dark energy, which is even more mysterious. Dark energy is causing the universe's expansion to accelerate, pushing galaxies apart. We have even less idea what it is than we do for dark matter. But that is a different topic. For now, the point is that the Milky Way, like all galaxies, is mostly made of things we do not understand. The visible stars, the gas clouds, the planets and moons and asteroids, everything we can see and touch is a minority component. The majority is invisible, detectable only through gravity. This does not make the visible parts less important. We are made of normal matter. Our existence depends on the properties of protons and electrons and the forces between them. Dark matter might provide the scaffolding, but normal matter is what creates complexity. Stars, planets, life. Still, it is worth remembering that we are living in a galaxy we can only partially see. Most of it is hidden from view, a vast dark halo surrounding everything we observe. The Milky Way does not exist in isolation. It is part of a larger structure, a group of galaxies bound together by gravity, the local group. There are about 80 known galaxies in the local group. The number keeps growing as astronomers discover more faint dwarf galaxies that were previously overlooked. Most members are small, dwarf galaxies with only a few million stars. But 2 galaxies dominate: the Milky Way and Andromeda. Andromeda, also known as Messier 31, is the nearest large galaxy. It is about 2.5 million light-years away. From Earth, it is visible to the naked eye as a faint smudge in the constellation Andromeda. Through a telescope, it is spectacular. A grand spiral similar to the Milky Way but larger, containing perhaps 1 trillion stars. Andromeda is approaching us. Not orbiting, approaching. The Milky Way and Andromeda are falling toward each other, pulled together by their mutual gravity. In about 4.5 billion years, they will collide, or rather merge. Despite containing hundreds of billions of stars each, Actual collisions between individual stars will be rare. Stars are so far apart that most will pass by each other without incident. But the gravitational interactions will be dramatic. The two galaxies will pass through each other, their shapes distorted by tidal forces. Stars will be flung out into long tails. Gas clouds will collide, compress, and trigger intense bursts of star formation. Then they'll fall back together, pass through again, gradually settling into a single, merged galaxy. The process will take a few billion years. The end result will be a large elliptical galaxy containing roughly 1.5 trillion stars, the combined populations of both galaxies. Astronomers have nicknamed this future galaxy Milky Way, or sometimes Milkdromeda, a blend of Milky Way and Andromeda. What will this mean for Earth? Probably nothing directly. The Sun and Earth will likely survive the merger unscathed. The chances of another star passing close enough to disrupt Earth's orbit are tiny. The distances between stars are so vast that even in a galactic collision, direct encounters are unlikely. But the night sky will change dramatically. As Andromeda approaches, it will grow larger and brighter. Eventually, it will dominate the sky, a huge glowing structure visible even during daytime. When the galaxies pass through each other, the sky will be filled with the light of newly forming stars, bright blue regions where gas clouds are colliding and fragmenting. The rate of supernovae will increase. The combined light from both galaxies will be spectacular. But there's a problem. The Sun is getting brighter. This has nothing to do with the merger. It's a normal part of stellar evolution. As the Sun ages, it gradually increases in luminosity. In about 1 billion years, maybe a bit less, the Sun will be bright enough that Earth's oceans will evaporate. The surface will become uninhabitable. Life as we know it will end, at least on Earth's surface. So by the time the Milky Way and Andromeda merge, Earth will already be a dead world. Humans, if we still exist, will need to have moved elsewhere. To Mars, perhaps, or the moons of Jupiter, or to other star systems entirely. If we're still around, if we've survived and spread beyond Earth, the merger will be an incredible event to witness. Civilizations observing from safe locations will see two galaxies combine, creating something new. But from Earth's perspective, assuming anyone is still here to observe, the merger will be a distant spectacle. Interesting, but not immediately threatening. The local group contains a third large spiral, Triangulum, also known as Messier 33. It's smaller than the Milky Way and Andromeda, with perhaps 40 billion stars. It's about 3 million light-years away. Triangulum might merge with Andromeda before Andromeda merges with the Milky Way. Or it might happen later. Computer simulations give different results depending on the initial conditions. Either way, all three galaxies will eventually combine into a single, large elliptical. The rest of the local group consists of smaller galaxies. The large and small Magellanic Clouds visible from the southern hemisphere are dwarf irregular galaxies orbiting the Milky Way. They're being slowly torn apart by tidal forces and will eventually be absorbed. There are dozens of dwarf spheroidal galaxies, small elliptical galaxies containing only a few million stars. Many of these are satellites of the Milky Way or Andromeda, orbiting the larger galaxies. New members of the local group are still being discovered. Faint dwarf galaxies are hard to detect. They don't emit much light, and they're spread out over a large area of sky. Only in recent years, with better surveys and telescopes, have we found many of them. The local group is gravitationally bound. Unlike the universe as a whole, which is expanding, the local group is held together by the gravity of its member galaxies. The expansion of space is happening around us, carrying distant galaxies away, but the local group itself is not expanding. This is important for the long-term future. As the universe continues expanding and dark energy pushes galaxies apart, the local group will become increasingly isolated. Distant galaxies will recede beyond the horizon, their light redshifted to undetectable wavelengths. Billions of years from now, observers in the merged Milky Way galaxy will look out and see almost nothing. A few small satellite galaxies nearby. But beyond that, darkness. All the other galaxies, billions of them, will have been carried away by cosmic expansion, now invisible. Future astronomers might conclude that the universe contains only one galaxy. They wouldn't be able to see the evidence that we can see today. No cosmic microwave background, no distant galaxies, no large-scale structure. This is one of the strange consequences of living in an accelerating universe. We're living in a special time, a time when we can see a large portion of the observable universe, when we can detect galaxies billions of light years away, when we can study the cosmic microwave background. Future civilizations won't have these advantages. But that's the far future. For now, we're part of the local group, one of many groups of galaxies scattered across the universe. And the local group is part of something larger still. The Virgo supercluster, a collection of galaxy groups and clusters, bound together on even larger scales. The Virgo supercluster contains roughly 100 galaxy groups, including our local group. It's about 110 million light-years across. At its heart is the Virgo cluster, a dense collection of about 1,500 galaxies. The local group is on the outskirts of the supercluster, falling slowly toward the Virgo cluster over hundreds of millions of years. But even this isn't the whole story. Recent work has shown that the Virgo supercluster is part of an even larger structure called Laniakea. Laniakea is a supercluster of superclusters, a vast region about 520 million light-years across, containing roughly 100,000 large galaxies. Our motion through space is determined by the gravitational pull of all this mass. The Milky Way is moving toward the center of Laniakea, along with everything else in the supercluster. Beyond Laniakea, the universe is filled with similar structures, superclusters separated by vast voids, regions of space that contain very few galaxies. The cosmic web, a filamentary structure of matter on the largest scales. Galaxies are concentrated in sheets and filaments, surrounding enormous voids that can be hundreds of millions of light-years across. These voids are not completely empty. They contain some galaxies, but they are far less dense than the filaments. This structure arose from tiny density fluctuations in the early universe. Regions that were slightly denser than average collapsed under their own gravity, pulling in more matter, growing into the filaments and clusters we see today. Regions that were slightly less dense became voids, emptied out as matter flowed toward the denser regions. The cosmic web is the largest structure in the universe. On scales larger than a few 100 million light-years, the universe looks roughly the same in every direction. homogeneous and isotropic, as cosmologists say. But on smaller scales, there's tremendous structure. Galaxies, clusters, superclusters, filaments, voids. The Milky Way is embedded in this structure, one galaxy among 2 trillion in the observable universe. The observable universe is a sphere about 93 billion light-years across, centered on Earth. This is larger than you might expect, given that the universe is only 13.8 billion years old. Light has had only 13.8 billion years to travel. So shouldn't the observable universe be only 27.6 billion light-years across? The difference is expansion. The universe has been expanding while light traveled. Objects that emitted light 13.8 billion years ago, shortly after the Big Bang, are now much farther away than 13.8 billion light-years due to the expansion of space during the intervening time. So the edge of the observable universe, the cosmic horizon, is currently about 46.5 billion light-years away in all directions, making the observable universe about 93 billion light-years across. That we can't see. Light from farther regions hasn't had time to reach us yet, or rather, it hasn't had time to reach us within the age of the universe. But the universe almost certainly extends beyond the observable horizon. It might be infinite. We don't know. We can only observe the part that's within our cosmic horizon. And within that observable volume, there are roughly 2 trillion galaxies, most smaller than the Milky Way, some larger. The Milky Way is above average, in the top 5% or so by size and mass. But compared to the largest galaxies, supergiant ellipticals like IC 1101, the Milky Way is small. IC 1101 is 60 times larger in diameter. Some elliptical galaxies contain tens of trillions of stars, 100 times more than the Milky Way. So the Milky Way is large compared to most galaxies, but small compared to the universe. One galaxy among 2 trillion, an island of stars in an ocean of space. Now we come home. We've traveled outward from Earth through the solar system into interstellar space, across the spiral arms, past the bulge and the black hole, through the halo, beyond the dark matter halo, out to the local group and the Virgo supercluster and the cosmic web. Now we reverse the journey. We pull back our view, watching Laniakea shrink, watching the cosmic web fade, watching the local group resolve into individual galaxies. Andromeda growing smaller, less prominent, the Virgo cluster disappearing into the distance. We fall back towards the Milky Way, watching it grow, watching the spiral structure become clear again. The disk, the arms, the bulge at the center glowing brightly. We descend towards the disk, passing through the halo, watching globular clusters drift by. Ancient stars on their long elliptical orbits. We cross into the disk, surrounded now by stars. Thousands of them scattered through space, each one a sun, possibly with planets, possibly with life. We're in the Orion Arm again, back in our neighborhood, the familiar stars. Sirius the brightest, Vega, Arcturus, Betelgeuse in Orion, the red supergiant that might explode any day now, cosmically speaking. Past the nearby stars, crossing those final light years, until we see a familiar yellow star. Not the brightest, not the largest. Unremarkable, really. One star among hundreds of billions, but it's our star, the Sun. And there, orbiting at one astronomical unit, the third planet, blue and white, covered in clouds and oceans, small, insignificant from a cosmic perspective, but home, Earth. We've completed the journey. From Earth out to the edge of our cosmic neighborhood, and back again. What have we learned? The Milky Way is vast, 100,000 light-years across, containing hundreds of billions of stars, trillions of planets. It's one of the larger galaxies in the universe, a grand spiral, beautiful and complex. But it's also small. One galaxy among 2 trillion. Part of the local group, which is part of the Virgo supercluster, which is part of Laniakea, which is part of the cosmic web, which fills the observable universe. Zoom in, and the Milky Way is immense, larger than 95% of all galaxies. Zoom out, and it's a speck, barely visible among countless others. Both perspectives are true. Both matter. The Milky Way is our home. Every star we see in the night sky belongs to it. Every constellation, every myth and story humans have told about the heavens. All of it is contained within this one galaxy. We are children of the Milky Way. The atoms in our bodies were forged in stars that lived and died billions of years ago. Their death scattered those atoms into space, into the gas clouds that eventually collapsed to form the Sun and Earth. We are, quite literally, made of stardust. The calcium in our bones, the iron in our blood, the carbon in our deoxyribonucleic acid. All of it was created in stellar cores through nuclear fusion. The Milky Way gave us the heavy elements necessary for rocky planets and complex chemistry. It provided a stable environment where the Sun could orbit for billions of years without catastrophic disruptions. It created the conditions necessary for life. And now, 13.8 billion years after the Big Bang, the universe has produced beings capable of understanding their place in it. Conscious observers who can look up at the night sky and comprehend what they're seeing. This is extraordinary. Out of unconscious matter, following blind physical laws, complexity emerged. Atoms organized into molecules, molecules into cells, cells into organisms, organisms into conscious beings capable of wonder. You are the universe knowing itself. You are a way for the cosmos to understand its own existence. That's not poetry. It's literal truth. You're made of atoms that have existed for billions of years, since shortly after the Big Bang. Those atoms were once in stars. Now they're in you, temporarily. When you die, they'll be recycled, returning to the environment, eventually perhaps into other living things, or into the earth, or scattered into space. But for now, they're arranged in a pattern that can think, that can observe, that can understand. The Milky Way is small compared to the universe. Earth is tiny beyond comprehension, and you, a single human on that tiny planet, are smaller still. But you're also precious, irreplaceable, unique. Because as far as we know, Earth is the only place where life exists. We might not be alone. The universe is vast, and probability suggests there might be other life out there somewhere. But we don't know. We haven't found it. Until we do, we have to assume we're rare, possibly unique. And that means what happens here matters. How we treat this planet, this small blue world, matters enormously. The Milky Way will continue orbiting, stars will be born and die. The galaxy will eventually merge with Andromeda. The universe will keep expanding. On cosmic timescales, nothing we do matters. But on human timescales, everything we do matters. We're the only voices we know of in the cosmic darkness, the only consciousness, the only beings capable of love and art and music and wonder. That's worth preserving, worth protecting. The Milky Way is 13 billion years old. It will continue for trillions of years, long after the sun dies, long after Earth is gone. The galaxy's story is vastly longer than ours, but we're part of that story. A brief chapter, perhaps, a few million years of human existence in a galaxy that will last trillions. But we're here now, conscious, aware, capable of understanding. That's enough. That's everything. When you look up at the night sky tonight, remember what you've learned. That band of light stretching across the darkness is the Milky Way, seen from inside. Those points of light are stars, each one a sun, many with their own planets. You're inside a galaxy, surrounded by hundreds of billions of stars, part of a structure 100,000 light-years across, located in a minor spiral arm 26,000 light-years from the center, orbiting a supermassive black hole every 225 million years. You're made of atoms forged in stars that died billions of years ago. You're a temporary arrangement of stardust, granted the extraordinary gift of consciousness. The universe is vast. The Milky Way is small. Earth is smaller. You are smaller still. But you are here. You exist. You can look up at the stars and understand what you are seeing. And that makes you remarkable. The Milky Way gave us everything. The heavy elements for rocky planets, the stable environment for life to evolve, the billions of years of relative calm necessary for complex life to emerge. We are the Milky Way's children, born from its dust and gas, shaped by its structure, held by its gravity. And now, after billions of years, the galaxy has produced beings capable of understanding it, capable of mapping its structure, measuring its size, tracing its history, predicting its future. We have come full circle. The universe, through us, knows itself. That is the meaning of the journey we have taken tonight. Not just to understand the Milky Way's size or structure, but to understand our place within it. We are small, but we are also part of something vast, something ancient, something beautiful. The Milky Way is our cosmic home, and home is where we belong. Thank you for taking this journey through our galaxy. If you found this meaningful, please like and subscribe. Your support helps create more explorations like this. And remember, when you look up at the night sky, you are not just seeing points of light. You are seeing our galaxy. You are seeing home. Good night, and may you never look at the Milky Way the same way again.